Elsevier Regional Science and Urban Economics 25, 1995, 607-630. Is public infrastructure productive? A Metropolitan Perspective Using New Capital Stock Estimates. John B. Criffield *, Martin P. H. Pangabean. Institute of Government and Public Affairs, University of Illinois, 1007 West Nevada Street, Urbana, Illinois 61801 USA. Received May 1993, final version received November 1994. Abstract. This paper studies the productivity of public investment within the context of a neoclassical growth model. We use recently developed estimates of public infrastructure from Criffield, Pangabean, Holtz-Eakin, Munnell, and the National Cooperative Highway Research Program, NCHRP, to calculate public and private sector investment rates. These infrastructure measures are combined with disaggregated data for the states and 282 metropolitan areas in order to estimate the growth model. The estimations show that public infrastructure, however measured, has at most a modest effect on factor markets, and an even smaller impact on growth in per capita income. Public infrastructure surely plays an important role in metropolitan economies. However, its marginal contribution is no more than, and may be less than, other forms of investment. Keywords: capital stock, economic development, economic growth, infrastructure, productivity, public sector JEL classification, RLL, H72, H54. 1. The adequacy of public infrastructure. THEADEQUACY of PUBLICINFRASTRUCTURE is AQUESTION at the CENTER of NATIONALAND local DEBATESONECONOMIC policy. CURRENTAND past ADMINISTRA * corresponding author. 0166-0462/95/$09.50 Copyright 1995 Elsevier Science BV. All rights reserved. SSDI 0166-0462/95, 02087X. 608. J. B. Criffield, MPH Pangabean/Reg Sci Urban Econ. 25, 1995, 607-630. Nations in Washington have made public investments central to their economic plans for the future. There is no consensus, however, as to how such plans affect the economy. Hulton and Schwab's earlier work, 1984, on the subject does not support the view that deficiencies in public infrastructure have caused the slowdown in U.S. growth in recent decades. Similarly, Holtz-Eakin, 1991, concludes that public infrastructure does not affect growth in state output at the margin, even though it remains essential to economic performance. Garcia-Milfi and McGuire, 1992, found that state and local expenditures on highways and education have positively significant, but relatively small, impacts on gross state product. However, a more recent paper, Garcia-Mill/ETAL, 1993, fails to find any relationship between state-level public investment and growth in gross state product. Examining growth in metropolitan employment and manufacturing output, Criffield, 1989, 1990, found small but positively significant effects of capital outlays by local governments, but not by state governments. In an extension of their 1984 work, Hulton and Schwab, 1991a, found further evidence to support their earlier conclusion that public infrastructure is only weakly connected to productivity growth. Indeed, with two exceptions, most recent work bolsters the view that public infrastructure has at most a modest impact on economic performance, no matter how the performance is measured. The exceptions are the findings of Aschauer, 1989, and Munnell, 1990. Both find substantial impacts of public capital on output. In particular, Aschauer's results imply a rate of return to public investment of 70%, Hulton and Schwab, 1991b. Point 1 THERE is no single way to show how public infrastructure affects the economy. The most direct approach defines infrastructure as an input in production and then proceeds to estimate the production function. Aschauer, 1989, does this using national aggregates, while Munnell, 1990, uses national and broad regional aggregates for private sector and public sector capital stocks, labor, and output. Garcia-Milfy and McGuire, 1992, adopt a similar strategy, but estimate production functions using state data. Each of these studies adopts COBB, DOUGLAS technology, but obtains very different estimates for the productivity of public capital. 2. We adopt a different strategy, and use a neoclassical growth model in conjunction with a disaggregated data set. The questions we address are whether different measures of public capital alter the estimation of model. For details of these and other works, see Hulton and Schwab, 1991a, and NCHRP, 1994, Section 1. The productivity parameter in question is B from a function such as Q equals AKZL, where Z is public capital. From B one can determine the marginal productivity and the rate of return to public investment. Aschauer, 1989, estimates B to be about 11.39, Munnell, 19,911, about 0.15, Duffy Dino and Eberts 11,991, about 0.08, and Garcia-Milfy and McGuire, 1992, about 0.04 for highways and 0.07 for education. J. B. Criffield, MPH Pangabian/Reg Sci Urban Econ. 25, 1995, 607-630. 609. PARAMETERS in general, and productivity measures for public capital in particular. THEASCHAUER, MUNNELL productivity estimates for public capital SEEM inordinately high, and these findings have BEEN criticized on methodological grounds, NOR have these findings held up to estimations based on state data. 40 URPOSE is to push the analysis farther. WHATHAPPENS if one uses local data. WHAT if, in addition to local data, one tries new measures of public capital infrastructure. These questions are analyzed below in depth. We confine the estimations to the period 1960 to 1977. In related WORK, Criffield and PANGGABEAN, FORTHCOMING, we find that a neoclassical growth MODEL fits the data for these years very well. TOOURKNOWLEDGE, OUR data are MORE disaggregated and are for a longer period than data used in previous WORK. These data we see OMBINE public sector and private sector infrastructure data OBTAINEDFROM several sources, including HOLTZ, EAKIN, Munnell, and the National COOPERATIVEHIGHWAYRESEARCHPROGRAM, and CHRP. See the appendix for details. We find that HOWEVER1 defines public infrastructure, its effect on factor MARKETS has BEENMODEST, and its effect on per capita INCOME has been very small, results that are consistent with HULTEN and Schwab, HOLTZ, EAKIN, and our earlier work. In WHAT follows, Section 2 describes the MODEL and presents results of estimation, and Section 3 draws conclusions from OUR findings. 2. Model and estimation DERIVATION of the MODEL is described elsewhere, so we go straight to the estimating equation. 5. OUR focuses the productivity of public capital, REPRESENTED by the EXPONENTAZ of the public capital stock in an underlying COBB, DOUGLASPRODUCTION function. This parameter is directly proportional to the coefficient OFLOGSZ in log Q, T, log Q, 0, equals 1 RR, log A, 0, plus 1 to 7 R, YT, 1, RR, AK, 1, 7R, AZ plus 1 AKAZAHL degree GSK plus 1 AKAL degree GS, 1, 7R, AH plus 1 AKAZAL degree GSHZ. See Tatum, 1991, for an analysis of bias from failure to adjust for non-stationarity. 4. In addition to Garcia Milfy and McGuire, 1992, see Criffield et al., forthcoming. This model is developed in Criffield and Pangabean, forthcoming, and in Criffield et al., forthcoming. Mankey et al., 1992, construct a similar model. These models are based on the original Solow, 1956, growth model. 610. J.B. Criffield. MPH. Pangabean. /REG. SCI-URBAN. Econ. 25, 1995, 607 to 630. 1. AK and AZ plus A. Log, plus G, 1, R, log Q, 0, 1. 1 AKAZAH. 1, 7R, RTS, 1, plus 1 AKAAH log L, T. THERE are other fundamental relationships embedded in EQ, 1. For example, the convergence hypothesis asserts that poorer regions catch up with wealthier ones, and in this model, the speed of convergence is a function of the coefficient of log Q, 0. The coefficient of log L, T, tests returns to scale, RTS equals 1 is constant returns, and the sum of coefficients for log, SK, log, SH, log, SZ, and log, 6 plus G, tests the COBB, DOUGLAS hypothesis in production. The coefficients can also be solved simultaneously to determine the production function parameters AK, AZ, and ET. EQ, 1, is estimated using both ordinary least squares, OLS, and two-stage least squares, 2SLS. OLS assumes that all variables on the right-hand side of the equation are exogenous. In principle, population growth, a proxy for labor force growth, and investment rates are unlikely to be exogenous across metropolitan areas for long time periods. This is because factors move freely across metropolitan boundaries, and their flows alter factor returns and per capita incomes in different places. To take into account this simultaneity between factor markets and the growth in per capita income, the left-hand side of EQ, 1, 2SLS models estimate reduced form population growth and investment equations separately, and predicted values from these estimations enter EQ, 1, as the second step of a 2SLS model. Data for the dependent variable consist of a single cross-section of metropolitan growth rates for the period 1960 to 1977. Observations include the 277 Standard Metropolitan Statistical Areas, SMSAs, defined by the USDEPARTMENT of Commerce in December 1977. Also included are areas that were separately defined as SMSAs in 1963. To maintain spatial consistency through time, county data were added or subtracted so that SMSA totals conform to the 1977 boundaries. When possible, data were collected for SMSAs, and include information for personal income, population, high school completion rates, manufacturing investment, local public outlays, and local taxes. Some data are only available by state, including capital depreciation rates, natural gas prices, electricity prices, unionization rates, average property taxes, and infrastructure data from Holtz-Eakin, 1992, Munnell, 1990, and NCHRP, 1994. 6. Public sector and private sector investment data are described in the appendix. All other data are described in Criffield and Pangabean, forthcoming. In this earlier paper the choice of period affected the rate of convergence, but not estimates of public sector productivity. To control for regional disparities created by oil price and other shocks in the 1970s, we include regional DUMMIES and prices for electricity and natural gas in the first stage factor market models. J.B. Criffield, MPH Pangabean/REG Sci Urban Econ. 25, 1995, 607 to 630. 611. The reduced form first stage models for the log of population growth, LG, and the log of the investment rate, LSK, include a large set of variables. LPOP60, log of metropolitan area population in 1960, LQ60, log of real metropolitan area per capita income in 1960, LS, log of a proxy for investment in human capital, LSZOC, log of local government's investment rate, and LState, log of state government investment rate, must appear in first stage regressions for LG and LSK since they appear on the right-hand side of EQ. 1. Variables serving to identify LG and LSK include LSTAX, log of state tax rate, LTAX, log of local tax rate, LSPT, log of average state property tax, LPELEC, log of electricity price, LPGAS, log of natural gas price, LUNION, log of unionization rate, and 9 regional dummies. The Pacific region is the excluded dummy. Output data are unavailable for metropolitan areas. However, income is a close proxy that we use in measuring per capita growth, left-hand side of EQ. 1, and as the denominator in measuring investment rates. Expected signs from estimating the growth model are clear from EQ. 1. Growth in per capita income increases with technological change, investment rates SK, ST, and SH, and with increasing returns to scale. It falls with population growth, capital depreciation, and initial period per capita income. The role of fiscal variables can be studied in the context of the first stage models. Tax variables LSTAX, LTAX, and LSPT shift factor demands to the left, or, equivalently, shift factor supplies to the left, thereby reducing LG or LSK. If public investment, LSZOC, state, complements private factors, then expected signs for LSZO and Z state are positive. A summary of variables is given in Table 1. 2.1 Population growth and investment. The benchmark models reported in Tables 2 to 4, models LG1, LSK1, GRO1, are estimated for the period 1960 to 1977. These models include the private and public sector investment and tax variables referred to as Criffield and Pangabean in the appendix, and provide a consistent framework for studying relationships between public sector and private sector investment and growth. Results with respect to public capital are little affected by our choice of period. The other population growth and investment rate models, LG2 through LG7, and LSK2 through LSK7, consider alternative measures of public investment, see the appendix. Models 2 and 3 use measures of public investment constructed from Holt-Zekins estimates of public capital. In Model 2, 5 specific public sector investments are included, whereas in Model 3 a total investment rate is used. Because 2 of the 5 public investments in Model 2 refer to education, this model excludes LSH. Model 4 includes investment in transportation based on Federal Highway Administration data. Model 5 includes alternative transportation-related variables. 612. J.B. Criffield, MPH Pangabean/REG Sci Urban Econ. 25, 1995, 607 to 630. Table 1 Summary of variables. Variable dependent variable, LQXX definition log of metropolitan area per capita income, Q, in year 19XX. The dependent variable in EQ, 1, is LQ77, LQ60. First stage variables, LPOP60 stacks LTAX LSPT. Log of metropolitan area population in 1960 log, stacks, where STAX is state taxes divided by state income log, tax, where TAX is local taxes divided by local income log, SPT, where SPT is the average effective property tax rate by state on existing single-family homes with FHA-insured mortgages. Log of electricity price, log of natural gas price, log of the state unionization rate. New England states, Middle Atlantic states, East North Central states, West North Central states, South Atlantic states, East South Central states, West South Central states, Mountain states, Pacific states. Omitted dummy. Alpalical gas Union D1 D2 pound 3 D4 D5 D6 D7 D8 D9 growth model, second stage. DOB. LGLSK. Compound annual growth in metropolitan area population from 1960 to 1977. Log, GPOP plus 1, log, SK, where S is the share of income invested by the private sector. J.B. Criffield, MPH Pangabian/REG Sci Urban Econ. 25, 1995, 607 to 630. 613. Table 1, continued, variable LSJ, definition. Log of the fraction of people 25 years old or older with at least 12 years of schooling. Log, GVO plus 6, where 6 is the depreciation rate, annual rate of convergence, or divergence, in per capita income, a function of the adjustment parameter, 70 parameter governing adjustment towards steady state. L, GLO plus, A, IT, AK, L, A1, A. Production function parameters for private capital, human capital, labor, and public capital. I returns to scale. RTS public capital. LSLOC. Log, SO, where S, is the share of local income invested in local public capital outlays. Log, S, where S is the share of state income invested in state public capital outlays. Holds EEC in higher education, state and local, by state. Log of average investment relative to average state income. Holds EEC in other education, local schools, state and local, by state. Log of average investment relative to average state income. Holds EEC in streets and highways, state and local, by state. Log of average investment relative to average state income. Holds EEC in sewerage and sanitation, state and local, by state. Log of average investment relative to average state income. Holds EEC in utilities, state and local, by state. Log of average investment relative to average income. Holds EEC in total, state and local, by state. Log of average investment relative to average state income. Federal Highway Administration, all governments, by state. Log of average investment relative to average state income. MUNU total state and local, by state. Log of average investment relative to average state income. LSTT. He H1 ed. He OED. He STR. He SO. He UT. He taught pub. FHA. MUN taught pub. 614. J.B. Criffield, MPH Pangabian/REG Sci Urban Econ. 25, 1995, 607 to 630. Table 1, continued, variable M on HIWAY definition. Munal Highway, state and local, by state. Log of average investment relative to average state income. Munal Water and Sewerage, state and local, by state. Log of average investment relative to average state income. Munal Other, state and local, by state. Log of average investment relative to average state income. Lane miles, all roads and highways, per capita, by state. Interstate highway lane miles, rural and urban, divided by total lane miles, by state. Air departures per capita, by state. LANE times air, network effect of road and air systems, by state. MUN WATSEW. MUN Auth. Lane 57. An NTWK. Notes, values are stated in $1982. Variables measure average values for the period 1960 to 1977. For example, SOC, the fraction of local income devoted to public investment, for each metropolitan area is a simple average for 1962, 1967, 1972, and 1977. SH, fraction of persons graduating from high school, is an average for 1960, 1970, and 1980. And so on. Years used in constructing variables reflect the availability of data. For lane miles, a quantity road index defined as lane, interstate highways, a quality road index defined as 1 to 57, air departures per capita, air, and the interaction, network, effects of these variables, NTWK. Models 6 and 7 integrate measures constructed from Munnell's public capital stock series. 3 conclusions emerge from the population growth models in Table 2. First, the benchmark model, LG1, is little changed by alternative measures of public investment. Second, public investment has little or no effect on population and employment growth. There may be some impact from LZLOC, which is the Crefeld-Pangasian measure of the composite rate of local government investment. However, state measures of public investment typically have little impact. These state measurements include the Crefeld-Pangasian measure, LSS8, estimates from Holtz-Eakin and Munnell, HEHIDE, HESTR, HEUT, MUN-Highway, MUN-WATSO, measures from the Federal Highway Administration, FHA, and measures of physical transportation infrastructure, lane, 1 to 57, NTWK. Exceptions where public spending positively and significantly affects population growth include spending on sewers and sanitation, HESO, other, MUNOTH, and air departures, air. Theory does not provide unambiguous guidance as to how public infrastructure affects labor market outcomes. J. B. Crefeld, MPH Pangasian/Reg Sci Urban Econ. 25, 1995, 607 to 630. 615. Table 2 Population Growth Model, Description. Independent Variable, D1 D2 D3 D4 D5 D6 D7 D8 LPO P60 LQ60. LSH. LG1. LG2. LG3. Basic Model. Holtz-Eakin 5 types of capital -0.033 -0.021 -0.015 -0.028 -0.010 -0.011 -0.018 -0.009 -0.007 0.004 -0.005 0.005 0.013 -0.011 -0.002 0.046, -4.01, -4.56, -4.09, -6.31, -2.18, -2.26, -2.98, -1.57, -4.42, 0.97, -3.72, 1.94, 4.77, -1.39, -0.88, 1.39. Holtz-Eakin total public capital -0.018 -0.013 -0.013 -0.025 -0.007 -0.001 -0.014 -0.009, -2.44, -3.10, -4.13, -6.37, -1.58, -2.93, -2.77, -1.73. -0.022 -0.015 -0.017 -0.025 -0.006 -0.006 -0.010 -0.006 -6.07, -5.63, -7.20, -7.75, -1.53, -1.85, -2.34, -1.42. LSTAX LTAX LPLICLP Gas L Union Constant Public Capital, LS Slow. L State. -0.006, -4.52, -0.0001, -0.04, 0.028, 6.07, minus 0.004, minus 3.66, 0.001, 0.19, 0.010, 5.85, minus 0.005, minus 1.75, minus 0.002, minus 0.83, 0.036, 1.58, minus 0.04, minus 3.27, 0.0003, 0.09, 0.029, 6.29, minus 0.002, minus 2.11, 0.005, 1.95, 0.012, 4.16, minus 0.007, minus 1.14, minus 0.005, minus 1.77, 0.086, 3.88, 0.005, 2.74, minus 0.012, minus 2.89, minus 0.007, 0.005, minus 2.32, 1.51. He h1 ed he oed he str he so he ut he tot pub. Minus 0.005, minus 2.04, 0.003, 1.79, 0.001, 0.77, 0.004, 1.02. Adjective R2 dummies model, description. Independent variable, D1 D2 D3 D4 D5. 0.504 10.42, 8255. LG4. 0.4119.52, 8232. LG5. 0.4577.44, 8253. FHA with LSLOC, LSZ Tate. Lane miles, air, network minus 0.030 minus 0.019 minus 0.017 minus 0.023 minus 0.014, minus 4.39, minus 5.16, minus 6.01, minus 6.10, minus 3.26. Minus 0.019 minus 0.014 minus 0.017 minus 0.023 minus 0.003. Minus 2.81, minus 3.50, minus 5.27, minus 6.17, minus 0.75. 616. J.B. Criffield, MPH Pangabian/REG Sci Urban Econ. 25, 1995, 607 to 630. Table 2, continued, model, description, independent variable. D6 D7 D8 LPO P60 LQ60 LSH LSTAX LTAX LPLICL Gas Lunion Constant Public Capital, LG4 LG5. FHA with LSOC, LS. Lane miles, air, network minus 0.011, minus 2.87, minus 0.011, 247, minus 0.015, minus 2.24, minus 0.010 minus 0.005 0.028 minus 0.008 minus 0.001 0.011 minus 0.003 minus 0.005 0.078, minus 6.07, 1.60, 6.06, minus 5.69, minus 0.27, 3.86, minus 0.47, minus 2.28, 2.42. Minus 0.005, 1.18, 0.010, 1.82. Minus 0.005, minus 0.89. Minus 0.1, 1, 7, minus 4.40, minus 0.001, minus 11.32, 0.027, 6.05, minus 0.005, minus 3.59, 0.002, 0.52, 0.008, 2.87, dash 0.008, 1.41, minus 0.001, 11.36, 0.072, 1.69. LS, LS. FHA lane. 0.005, 2.74, minus 0.009, 1.33, minus 0.006, 122. 0.005, 2.95, minus 0.007, 1.53, minus 0.004, minus 0.64, 11.013, 0.23, 0.012, 2.00, minus 0.002, minus 0.64. 1 to 57. Air NTWK. Adjective R, dummies model, description. 0.4939.011, 8251. LG6. Munel total private capital and total public capital. 0.5536.92, 8248. LG7. Munel total private capital and 3 types of public capital minus 0.028, minus 3.37, dash 0.021, 4.15, minus 0.020, minus 5.33, minus 0.029, minus 7.55, minus 0.006, 1.22, minus 0.010, minus 3.33, minus 0.012, minus 2.53, minus 0.01, 9, 1.91. 0.006, minus 3.52. Independent variable, D1 D21, 3 D4 D5 D6 D7 D8 LPO P60. Minus 0.1, 17 minus 0.1, 13 minus 0.1, 14 minus 0.024 minus 0.005 minus 0.008 minus 0.013. Minus 2.26, minus 2.67, minus 4.18, minus 5.55, 1.02, minus 2.39, minus 2.46. Minus 0.007, 1.35. Minus 0.004, minus 3.29, 0.0004, 0.13, 0.030, 6.34, minus 0.002, minus 2.13. LQ60. LSH stacks. Minus 0.002, minus 0.50, 0.029 16.21, 0.004, minus 2.51. J.B. Criffield, MPH Pangabian /REG Sci Urban Econ. 25, 1995, 607-630. 617. Table 2, continued, model, description. LG6 LG7. Munel total private capital and total public capital 0.005, 1.96, 0,010, 3.06, minus 0.008, minus 1.25, dash 0,004, 1.64, 0,071, 4.20. Mun total private capital and 3 types of public capital 0.005, 1.97, 0.17, 4.81, minus 0.004, minus 0.69, 0.002, 0.51, 0.67, 3.79. Independent variable, LTA exlpaliklp gas lunion constant public capital, mun tot pub mun h1way mun watsEW mun auth. Minus 0.001, minus 0.41, minus 0.001, minus 0.59, minus 0.0004, minus 0.64, 0.003, 2.22, 0.494, 10.14, 8243. Adjective are dummies. 0.4557.54, 8253. Notes: the dependent variable is LG, the log of GVOP plus 1, where GVOP is the compound annual growth in metropolitan population over the period 1960 to 1977. The null hypothesis of no heteroscedasticity is rejected at the 5% level in all regressions reported in the table using the Briesk-Pagan-Godfrey, BPG, and Gleichzer tests. White's heteroscedastic consistent covariance matrix estimation is used to correct estimates for an unknown form of heteroscedasticity. Dummies refer to F-tests of the joint hypotheses that D1 equals D2, equals D8 equals 0, D9 for the Pacific region is the omitted dummy. For comparison, F, 8, 120, equals 2.66 at the 1% level of significance. Numbers in parentheses refer to degrees of freedom in the numerator and denominator. Variables are defined in the text, and in table I numbers in parentheses are two-tailed t-statistics for the null hypothesis that the coefficient is 0. Since these OUTCOMESDEPEND in part O and the DEGREE of COMPLEMENTARITYBETWEENLABORANDPUBLIC capital, as well as the CONSUMPTION value of public SPENDING. THE usually XPECTATION is that the effect is positive. THEMIXED results suggest that the role of public capital is EITHER subtle or relatively weak. THIRD, state taxes, BUTNOT local taxes, RNEGATIVELYAND significantly RELATED to POPULATION growth in all SEVEN models. In some MODELs the local tax coefficient is POSITIVEAND significant. BUT this occurs in cases WHERETHERE is NO local PUBLICINVESTMENT term. In these instances the local tax coefficient MAYPIC-UPA local INVESTMENT effect. DATAFROMTHRE sources are used to CONSTRUCTVARIATIONS of the DEPENDENTVARIABLE log S in the PRIVATE, SECTORINVESTMENTMODELS, TABLE3. THEBENCH, MARKMODEL, LSK, LA, AND several OTHERMODELS use METROPOLITAN, AREA. 618. J. B. Criffield, M. Ph. Pangabian/Reg Sci Urban Econ. 25, 1995, 607-630. Table 3 Investment Model, Description. Independent Variable, D1 D2 D3 D4 D5 D6 D7 D8 LPOP60 LQ60 LSH LSP Tilbalikl Gas Lumion Constant Public Capital, TS Zlock LSK Law LSK LB LSK LC. Basic Model. BEA Total Private Capital minus 0.396, minus 2.99, minus 0.568, minus 7.20, minus 0.092, minus 1.62, minus 0.052, minus 0.81, 0.414, 4.03, 0.427, 3.72, 0.467, 3.52, 0.387, 3.79, minus 0.020, 1.75, minus 0.066, 1.13, minus 0.041, minus 0.43, 0.420, 6.05, minus 0.077, 1.06, 0.027, 0.17, minus 0.121, minus 2.09, minus 2.514, minus 3.85. BEAMFG Capital 0.793, 2.91, 0.456, 2.42, 0.8746.21, 0.355, 1.71, 0.271, 0.99, 0.334, 1.29, -0.001, 0.005, minus 0.0181 to 0.07, 0.039, 0.87, -0.729, minus 2.97, minus 0.776, minus 1.58, -0.026, minus 0.11, minus 0.343, minus 2.05, 0.025, 0.10, 0.052, 0.28, minus 2.442, 1.76, 1.530, minus 4.75, 1.834, I 0.15, 0.355, 2.91, minus 0.113, minus 0.79, minus 0.583, minus 2.72, minus 0.054, minus 0.24, minus 0.042, minus 0.15, minus 0.706, minus 2.54, 0.052, 1.55, minus 0.941, minus 4.69, minus 0.379, minus 1.39, 0.434, 2.66, 0.217, 1.48, 0.542, 1.72, minus 0.711, minus 4.94, 0.896, 0.54. Stat Adjective R2 Dummies Model, Description 0.013, 0.10, 0.040, 0.14, 0.2046.32, 8256. LSK2 0.018, 0.58, 0.075, 0.62, 0.798 26.43, 8253. LSK3 minus 0.095, 1.09, 0.808, 2.32, 0.711 32.86, 8253. LSK4 Holtz-Eakin 5 Types of Capital. Holtz-Eakin Total State Public Capital minus 0.135, minus 0.41, minus 0.023, minus 0.12, 0.538, 3.66, 0.377, 2.03, 0.137, 0.47, 0.443, 1.66, 0.396, 1.40, 0.109, 0.47, 0.032, 0.74, minus 0.568, minus 2.28. FHA with LS slow, LS state. Independent variable, D1 D2 D3 D4 D5 D6 D7 D8 LPO P60 LQ60. 0.510, 1.12, 0.352, 1.55, 0.802 Q4.11, 0.4411 2.02, 0.2671 0.98, 0.4761 1.71, 0.577 1.88, 0.0131 0.05, 0.040, 0.87, minus 0.698, minus 2.26, minus 0.164, minus 0.52, minus 0.078, minus 0.42, 0.601, 4.20, 160, 0.75, 0.002, 0.01, 0.138, 0.53, 0.092, 0.30, minus 0.342, 1.22, 0.036, 0.85, minus 0.500, minus 2.02. J.B. Criffield, MPH Pangabian/Reg Sci Urban Econ. 25, 1995, 607 to 630. 619. Table 3, Continued, Model, Description. LS2 LSK3 LSK4. Holtz-Eakin 5 Types of Capital. Holtz-Eakin total state public capital minus 0.648 minus 0.203 minus 0.062 0.864 0.055 minus 4.203, 1.41, minus 0.87, minus 0.35, 2.61, 0.31, minus 3.11. FHA with LSO cent, LSZSAE. Independent variable, LSH LSPT minus 0.088, minus 0.33, Bullet minus 0.009, minus 0.33, Gas 1.063, 2.67, Lumion 0.003, 0.02, Constant minus 2.368, 1.23, Public capital, he hide he oed he str he so he uthe, to tpub fha. Minus 0.748, 1.62, 0.020, 0.09, 0.146, 0.80, 0.623, 1.81, 0.059, 0.33, 1.334, 0.40. 0.282, 1.47, minus 0.314, 1.42, 0.294, 1.91, minus 0.124, 1.30, 0.048, 0.77, minus 0.146, minus 0.49. LS equals low cent. LS state. Minus 0.391, minus 0.89, 0.004, 0.03, 1.083, 1.89, 0.2115.59, 8252. LSK7. Adjective R2 Dummies Model, Description. 0.1883.32, 8233. LSK5. 0.2004.65, 8254. LSK6. Lane miles, air, network. Munel total private capital and total public capital 0.250, 1.43, minus 0.135, minus 1.08, 0.168, 2.67, 0.305, 3.16, 0.678, 4.27, 0.545, 4.70, 0.282, 2.59, 0.547, 5.11, minus 0.033, minus 2.62, minus 0.107, 1.32, 0.078, 0.79, 0.233, 2.50, minus 0.497, minus 5.40, minus 0.764, minus 4.79, 0.049, 0.55, minus 2.139, minus 5.06. Munel total private capital and 3 types of public capital 0.561, 2.51, 0.114, 0.84, 0.359, 4.79, 0.331, 3.83, 0.559, 3.48, 0.515, 4.53, 0.184, 1.73, 0.500, 3.83, minus 0.014, minus 1.22, minus 0.060, minus 0.76, 0.078, 0.86, 0.256, 2.31, minus 0.638, minus 5.95, minus 0.895, minus 5.01, minus 0.180, minus 2.65, minus 1.466, minus 3.74. Independent variable, 01 D2 03 D4 D5 D6 D7 D8 LPO P60 LQ60 LSH LSP Tilpaliclp gas Lungian constant. 0.126, 0.38, 0.030, 0.16, 0.632, 3.74, 0.181, 0.72, 0.130, 0.47, 0.176, 0.68, 0.094, 0.34, 0.191, 0.69, 0.041, 0.96, minus 0.457, 1.74, minus 0.799, minus 1.77, 0.061, 0.26, 0.007, 0.04, 0.430, 1.31, 0.080, 0.51, minus 1.047, minus 0.38. 620. J. B. Criffield, MPH Pangabian/Reg Sci Urban Econ. 25, 1995, 607 to 630. Table 3, Continued, Model, Description. LSK5 LSK6 LSK7. Lane miles, air, network. Munel total private capital and total public capital minus 0.034, minus 0.45, 0.830 13.45, 8,254. Munel total private capital and 3 types of public capital 0.059, 2.36, 0.21, 1.09, minus 0.151, minus 3.24, 0.869 20.03, 8,244. Public capital, Mun Tot Pub Mun Hiway Mun Watsew Mun Auth LS. Lane 57 Air NTWK. 0.014, minus 0.11, 0.627, 1.58, 0.235, 0.51, 6.210, minus 1.62, 0.109, 0.35, minus 0.133, minus 1.02. Adjective R2 dummies. 0.2203.46, 8,249. Notes, the dependent variable is LSK, the log of the share of income invested by the private sector. In models 1b, 1c, 6, and 7 the dependent variable is calculated from state, as opposed to metropolitan, data. The null hypothesis of no heteroscedasticity is rejected at the 5% level in all regressions reported in the table using the Briesk-Pagan-Godfrey, BPG, and Gleichzer tests. White's heteroscedastic consistent covariance matrix estimation is used to correct estimates for an unknown form of heteroscedasticity. Dummies refer to F-tests of the joint hypotheses that D1 equals D2 equals D8 equals 0, D9 for the Pacific region is the omitted dummy. For comparison, F, 8, 120, 2.66 at the 1% level of significance, numbers in parentheses refer to degrees of freedom in the numerator and denominator. Variables are defined in Table 1. Numbers in parentheses are two-tailed t-statistics for the null hypothesis that the coefficient is 0. INVESTMENT in MANUFACTURINGTOCALCULATETHEPRIVATE, SECTORINVESTMENTRATESK, the Crefeld-Pangabien measure described in the appendix. The exceptions include Model LSKLB, which uses BEA total state private sector investment, Model LSKLC, which uses BEA state manufacturing investment, and Models LS6 and LSK7, which use Munnell's estimates of total state private investment. There are no consistent relationships between PUBLIC, SECTORINVESTMENTANDPRIVATE, SECTORINVESTMENT in THESEMODELS. FOREXAMPLE, THERE is NOCLEARRELATIONSCENTINTRANSPORTATIONVESTMENT in STRETSANDHIGHWAYSINMODELLSK2, HESTR, is POSITIVEANDSIGNIFICANT, as is MUN, HIWAY in LSK, 7. However, coefficients for other transportation variables are insignificant, FHA in LSK, 4, ANDLANE, air, and NTWK in LSK, 5, AND1 to 57 HASASIGNIFICANTLYNEGATIVESIGN in LSK, 5. SIMILARLY, state is POSITIVEANDSIGNIFICANT in MODEL1CBUTNOT in MODEL1A, EVENTHOUGHTHESEMODELSUSE. J. B. Crefeld, MPH Pangabien/REG Sci Urban Econ. 2.5, 1995, 607-630. 621. Table 4 Growth Models in Per Capita Income Model, Description, GRO1A, 2SLS, Restricted, GRO1B, 2SLS, Restricted, BEA Total Private Capital, 0.025, 0.98, 0.194, 3.97, -0.123, -2.71, -0.689, -22.55, 0.044, 7.38, 1.086, 8.85, GROIC, 2SLS, Restricted, BEA MFG Capital. Independent Variable, LSK LSH. L. BOP plus 6. LQ60 LPOP60 Constant Public Capital. -0.0200.181 -0.125 -0.676 0.0431.148 1.21 A 3.44 -2.88 -20.45 7.10 8.92 0.0050.178 -0.096 -0.690 0.0431.127 0.55 3.54 -2.36 -19.40 7.33 9.29 Stickles state. Adjective R2COBB, Douglas, TAK Audit. -0.019, 1.06, -0.018, -0.56, 0.760 1.32 0.066 -0.024 0.226 0.898 -0.026 1.46 -0.070 -2.78 0.7800, 0.600, 0.0690, 0.031, 0.239, 0.902 minus 0.032 minus 0.086, 1.054, 2.89, 2262, minus 0.53 minus 2.09 GRO3, 2 SLS, unrestricted, holds econ, total public capital, 0.038, 0.193 minus 0.029 minus 0.672, 0.042, 1.622, 1.63, 3.25, minus 0.62, minus 22.37, 7.41, 8.27, minus 0.027, 1.53, minus 0.060, minus 2.81, 0.780, 0.730, 0.069, 0.007, 0.226, 0.932 minus 0.034 minus 0.076, 1.055, 2.68, 2262, 0.30 minus 2.20 GRO4, 2 SLS, restricted, FHA with LS, LSS, E. A public. AOC as AE. RTSD. Minus 0.024 minus 0.022 1.054 4.19, 2265, 2.65 minus 1.47 GRO2, 2 SLS, restricted, holds econ, 5 types of capital, 0.031, 1.50. Houseman B. LSKRC LGRC. Model, description. Independent variable, LSKLS. L, BOP plus 6. LQ60 LPOP60 constant. Minus 0.020 minus 0.593 0.039 1.438. Minus 0.67. Minus 13.85, 6.82, 14.12. Minus 0.0030, 0.181 minus 0.095 minus 0.702, 0.043 1.206. Minus 0.20, 3.21, minus 2.14, 24.4, I, 7.38, 3.83. 622. JB. Criffield. MPH. Pangabian. /REG. URBANECON. 25, 1995, 607 to 630. Table 4, CONTINUED, Model, Description, GRO2, 2 SLS, Restricted, holds econ, 5 types of capital, 0.010 minus 0.054 0.022 0.010 0.001. GRO3, 2 SLS, unrestricted, holds econ, total public capital, minus 0.028, 111. GRO4, 2 SLS, restricted, FHA with LS low cent, LS Tate. PUBLIC capital, he H1 ed he OED he STR he so he UT he taught pub FHA LSLC LS. 0.56, minus 2.18, 1.69, 0.80, 0.11. Minus 0.011, 023, minus 0.026, 1.50, minus 0.046, 089. Adjective R2 Cobb Douglas AAKA, at Apamic Allied. AOEOASRRASEW or ATOTPUBRTSD. 0.778 0.18 0.053 0.0511 0.031 0.017 minus 0.087 0.035 0.016 0.001 0.779 1.96 0.065 0.0430 0.221 0.861 0.032 1.0487.33 2262 3.38 to 1.77 GRO6 OLS restricted Munal total private capital total public capital minus 0.006 044 0.136, 3.47, -1.20, minus 3.51, minus 0.669, 2139, 0.042, 7.57, 1.278, 14.20. 0.778 1.05 0.071 to 0.004 0.228 0.935 AHA 0.014 ALOC minus 0.033 A, E minus 0.058 1.0547 7.52 2261 3.62 to 1.94 GRO7 2 SLS restricted Munal total private capital and three types of public capital, minus 0.013 0.122 minus 0.101 minus 0.662 0.042 1.295, minus 0.66, 2.79, minus 2.37, minus 17.51, 7.22, 14.89. Houseman LSKRC LGR 1.0644.90, 2242, 3.07 minus 0.44 GRO5, 2 SLS, restricted, lane miles, air, network. Variable. Model, description. Independent TSK LSH. L, GPOP plus 8. LQ60 LPOP60 constant. 0.005, 0.35, 0.169, 3.40, minus 0.086, minus 2.33, minus 0.697, minus 25.64, 0.043, 7.43, 1.148, 9.21. JB. Criffield, MPH. Pangabian. /REG. Psi URBANECON. 25, 1995, 607-630. 623. Table 4, CONTINUED, Model, Description, GRO5, 2 SLS, Restricted, Lane Miles, Air, Network, GRO6, OLS, Restricted, Munal total private capital, total public capital, minus 0.010, 077. GRO7, 2 SLS, Restricted, Munal total private capital and three types of public capital, 0.010, 0.93, 0.001, 0.13, minus 0.019, 204. Public capital, Mun Tot Pub Mun HIWAY Mun Watso Mun Auth LSLOC LS. Minus 0.028, 156, minus 0.060, minus 2.64, 0.780 1.620 0.070 0.0060 0.215 0.944 0.778 1.29 0.065 minus 0.008 0.173 0.901 minus 0.012 dash. Adjective R2 Cobb Douglas 0.782 1.76 0.064 minus 0.017 0.160 0.922 0.013 AKIAI A public. A talk A. Arrow R. AHIWAY AWTSEW. Minus 0.035 minus 0.076. Dash. 0.002. 0.0251.0552.89, 2253, minus 0.31 minus 2.37. AOTH. RTSD. Minus 1.0556.98, 2262, 3.43 to 1.96. Minus 1.0532.46, 2263, minus 0.49 minus 2.21. Houseman. LSKRC LGRC. NOTES, the dependent variable is LQ77, LQ60, which is the log of per capita personal income in 1977 for a given metropolitan area minus the log of per capita personal income in 1960 for the same area. All models are corrected for heteroscedasticity, see tables 2 and 3. In all cases either the BPG test, Gleicher test, or both are rejected at the 10% level or less, although there is much less heteroscedasticity in these regressions, as reflected in the significance levels for BPG, Gleicher, and other tests, than in the factor market models of tables 2 and 3. COBB, DOUGLAS refers to the t-statistic testing whether the sum of a set of coefficients equals 0, see text. If the null hypothesis is accepted, then this restriction is imposed in estimation. All Houseman and NAKAMURA test statistics are estimated from models corrected for heteroscedasticity. LSK, R and LG, R are residuals from estimating LSK and LG, first stage estimations, and are used to test endogeneity for LSK and LG separately. Godfrey, 1989. Numbers in parentheses are t-statistics. HF statistics, with degrees of freedom in parentheses. Wallace reported are t-statistics. A returns to scale. 624. J. B. Criffield, MPH Pangabian /REG Sci Urban Econ. 25, 1995, 607-630. Similar dependent variables. In general, public sector investing bears no clear relationship to investment in the private sector. The same holds for taxes. The average state property tax rate, LSPT, shows no clear pattern. Its coefficient is negative, as expected, but not significant in most models, but is positive and highly significant in models using BEA and Munell data. 2.2 Growth models. The neoclassical growth model in EQ1 is the core of the analysis. All variables used in first stage and second stage estimations are developed with this equation in mind. Results from estimating the growth model are presented in Table 4. Variations GRO1 through GRO7 correspond to the population growth and investment models. In all but one case, GRO6, we reject at approximately the 5% level or less the joint hypotheses of exogeneity in labor and capital flows. See the Houseman tests in the table. Consequently, all models in Table 4 except for GRO6 are two-stage least squares, 2SLS, estimations. GRO6 is ordinary least squares, OLS. When exogeneity of labor and capital is tested separately, see LGR for labor and LSKR for capital in Table 4, exogeneity is rejected for both factors in most cases. Exceptions are models using BEAOR Munell data. For these exceptions, GRO1B, 1C, 6, 7, only labor is endogenous. In all but one case, GRO3, we accept the Cobb-Douglas specification. See the COBB, DOUGLAS tests in the table. In these cases we impose the COBB, DOUGLAS restriction regarding the sum of coefficients. All models test positively for heteroscedasticity at the 10% level or less based on Brioche PAGAN, GODFREY and Gleicher tests, and estimations are corrected for this problem. There are regularities common to all models. During the study period there was strong convergence in real per capita metropolitan income at the rate of 5%, 7% per year, see LQ60 in Table 4. All models also indicate increasing returns to scale of about 1.05, CLPOP60 and RTS, returns to scale. There are also regularities with regard to the signs and significance of individual coefficients. Per capita income growth was positively influenced by skill accumulation, LSH, and negatively influenced by population growth and capital depreciation, GPOP +6. Coefficients for these terms are, with few exceptions, statistically significant. Coefficients for private sector and public sector investment are typically insignificant. The coefficient of private investment, LSK, is significant with the expected positive sign in only 2 cases, GRO2, GRO3. The contribution of public investment is even more doubtful. Its coefficient is J. B. Criffield, MPH Pangabian/Reg Sci Urban Econ. 25, 1995, 607 to 630. 625. Significant with the expected positive sign only once, HESTR in GRO2. In several cases its coefficient is significantly negative. The coefficient estimates are solved simultaneously to find the implied production function elasticities, AI, and these are reported in the table. Many of the public sector elasticities are negative, which means literally that incremental public investments have a negative return. Even using our disaggregated metropolitan data, however, it is difficult to measure absolute sizes of marginal factor products. A qualitative assessment indicates that the returns to labor and human capital, for a given percentage increase in an input, are substantially higher than to private physical capital, and that returns in the public sector are very small if not negative. In short, the measured impact of public investment on metropolitan economies is weak. Public investment had a modest effect in labor markets, especially local public investment, but not in capital markets. However, public investment had little or no effect on growth in per capita income, either indirectly through factor markets or directly through rates of public investment. 3 conclusions. This paper studies the productivity of public investment within the context of a neoclassical growth model. We use several recently developed estimates of public infrastructure, those from Criffield and Pangabian, Holtz-Eakin, Munnell, and NCHRP. From these measures we calculate public sector and private sector investments necessary in estimating a modified neoclassical growth model. These infrastructure measures are combined with other data that are more disaggregated than used in previous research. The period 1960 to 1977 is a benchmark to standardize the estimations, since we found that data for this period fit EQ1 well. However, conclusions regarding the productivity of public capital are not changed when other periods are considered. Within this model we test a wide range of public and private investment measures. In general, there is strong evidence for the factor market models, first-stage regressions, especially for population growth, and also for the neoclassical growth model, second-stage regression. In most cases these estimations show that public infrastructure, however measured, has at most a modest effect on factor markets, and an even smaller impact on growth in per capita income. Most infrastructure coefficients in the growth models are statistically insignificant. Of those that are significant, more are negative than positive, contrary to the view that new government-sponsored investments have positive marginal products. In most cases the implied production elasticity for private capital exceeds those for public infrastructure. Local. 626. J. B. Criffield, MPH Pangabian/Reg Sci Urban Econ. 25, 1995, 607 to 630. Public investment appears to benefit labor and employers more than does investment by state government. However, neither state nor local investment led to growth in per capita incomes. These findings are consistent with the views of Hulton and Schwab and Holtz-Eakin that rates of return to public and private investment are roughly the same, and that marginal investments by state or local government will not generate spectacular ABOVE, MARKET returns. We are also doubtful that there are substantial unexploited externality gains from public investment. If there were unexploited gains, one would expect returns in metropolitan areas from state investments to exceed those from local investments, since presumably states can internalize gains that spill over the boundaries of cities. In fact, we find that local infrastructure contributes more to growth, or detracts less from growth, than does state infrastructure. Nor do we find that metropolitan areas benefit from network externalities, a possibility mentioned by Hulton and Schwab, 1991a. OUR results are noteworthy since we use a different model and estimation strategy than work that estimates production functions directly or that studies growth accounting. We use more disaggregated data than earlier work, and consider a wider array of public and private investment measures. OUR findings corroborate the work of Hulton and Schwab, Garcia-Milland and McGuire, DUFFY, DENO and Eberts, Holtz-Eakin, Criffield, and Pangabian, and others. Public infrastructure surely plays an important role in metropolitan economies. HOWEVER, its marginal contribution is no more than, and may be less than, other forms of investment. Acknowledgements. We wish to thank Randall W. Eberts, Therese J. McGuire, John M. Quigley, and anonymous referees of the journal for many valuable comments that have substantially improved earlier versions of this paper. Appendix: Investment and Taxation. This appendix describes public sector and private sector investment and taxation data and sources used in the paper. OTHER data and their sources are described in the appendix to Criffield and Pangabian, forthcoming. In most cases deflation is by the CPI, 1982 to 1984 equals 100. FHA data are deflated by the implicit GNP deflator, and data from BEA, Holtz-Eakin, and Munnell came to us deflated by BEA deflators. Data from the NCHRP project are more fully described in NCHRP, 1994. J. B. Criffield, MP.H. Pangabian/Reg Sci Urban Econ. 25, 1995, 607 to 630. 627. A.1 Public Sector Investment and Taxation. 1. Criffield and Pangabian taxation and public sector investment rates are defined separately for each metropolitan area and each state for the years 1962, 1967, 1972, and 1977. Local taxes include all local government taxes collected within an SMSA, and state taxes include all state government taxes. Similarly, local public investment includes all capital outlays of local governments within an SMSA, and state public investment includes all capital outlays of state government. Annual tax and investment rates are calculated by dividing these measures of taxation and investment by metropolitan area or state total personal income. Data years are matched as closely as possible. An alternative measure of state taxation is the average effective property tax rate for the years 1962, 1966, 1977, and 1980. Sources include U.S. Department of Commerce, Bureau of the Census, Census of Governments, Volume 4, Compendium of Government Finances, and Volume 5, Local Governments in Metropolitan Areas, 1962, 1967, 1972, and 1977, Advisory Commission on Intergovernmental Relations, Significant Features of Fiscal Federalism, 1980-81 edition. 2. Holtz-Eakin 1992, provides capital stock estimates by state for combined state and local governments. These include estimates for higher education, HEHIDE, local schools, HEOED, streets and highways, HESTR, sewerage and sanitation, HESO, utilities, HEUT, and total state and local public capital, HETOTPUB. For each capital stock category for each state we calculate the average net investment flow for the period 1960 to 1977 by subtracting the stock estimate in 1960 from the stock estimate in 1977, dividing by 17, and dividing this flow estimate by average state personal income for the period. These estimates differ from those of Criffield and Pangabian in two fundamental ways. First, Criffield and Pangabean measure investment and taxation for metropolitan areas as well as states. Holt-Zieken's estimates are state aggregates. Second, Criffield and Pangabean's measurements are actual values for capital outlays from the Census Bureau. Holt-Zieken's are estimates that are derived from BEA national capital stock values and from Census Bureau values for public expenditures and capital outlays. 3. Federal Highway Administration. The FHA collects annual data on all road expenditures by state. These data are totally independent of the Census Bureau's measures of capital outlays on highways, and were compiled as part of the NCHRP project. These FHA data are published annually in Highway Statistics. For the 628. J. B. Criffield, MPH Pangabean/Reg Sci Urban Econ. 25, 1995, 607 to 630. Years 1960 to 1977, we construct the average annual highway capital outlay for each state, and divide this by average state income for the period. THEFHA also collects information on lane miles, and these data are included in the NCHRP dataset. We use lane mileage for all roads and for interstate highways, by state for 1984, the earliest year available. Per capita values are based on 1980 state populations. For air departures, these data are average annual total departures per state over the period 1972 to 1977. Data for earlier years were not available. These data originate from the Federal Aviation Administration and are included in the NCHRP dataset. Per capita values are based on 1980 state populations. 5. Munnell. These data were made available by Leah Cook of the Federal Reserve Bank of Boston, and are described in Munnell, 1990, Appendix A. Data are combined state and local capital stock estimates for highways, MUN-Highway, water and sewer systems, MUN-WATSO, and other capital, MUN-Auth. To find average investments, we subtract stock values in 1969, the earliest year available, from the stock value in 1977, divide by 8, and divide this average flow by average state income over the period. The relationships between Munnell's estimates and those of Holt-Zieken are considered in Holt-Zieken, 1992. These estimates differ in how national BEA stock estimates are allocated to states. Munnell adopts a complicated weighting scheme where a state's share of the national state and local GOVERNMENT capital stock equals its share of state and local public capital SUMMED over all states. 7. Holt-Zieken calculates a state's weight as its share of state and local public expenditures, a broader category than capital outlays. Unlike the Criffield and Pangabean measures, which are city-specific and represent actual values, the Munnell estimates are available only for states and are derived from state and national aggregates. A.2 Private sector investment. 1. Criffield and Pangabean metropolitan area private sector investment data are only available for manufacturing industries. Our data represent new capital expenditures for total manufacturing for the years 1963, 1967, 1972, and 1977. The annual 7. What a paradox! Combined state and local public capital stocks are generated in order to weight a BEA national estimate of state and local capital, so as to estimate a state's public capital stock. Munnell's estimates of state and local public capital are generated each year using combined state plus local capital outlays from the census. Investments before 1958 are not counted. J. B. Criffield, MPH Pangabean/Reg Sci Urban Econ. 25, 1995, 607 to 630. 629. Private sector investment rate is defined as new capital expenditures divided by metropolitan area income. Numerator and denominator values are matched as closely in time as possible. To the extent that investment in manufacturing is directly proportional to total private sector investment, there would be no bias in estimation because our model is in logarithms. The factor of proportionality would be reflected in the regression constant. Depreciation rates are by state and are defined as depreciation charges divided by beginning of year gross book value of depreciable assets for total manufacturing in 1977. Data by state for earlier years and for other types of capital are not available, so we use these depreciation rates for all types of capital. Manufacturing data are from USDEPARTMENT of COMMERCE, Bureau of the Census, Census of Manufactures, Area Statistics, 1963, 1967, 1972, and 1977, and Subject Series, I-977. 2 NCHRP and MUNL alternative source of private sector investment comes from NCHRP, 1994. NCHRP begins with BEAS National Capital Stock Estimates by Industry. Each year national stocks are allocated to states based on a state's share of total gross state product, less indirect business taxes, SUMMED over all states. In our work we use NCHRP's private capital stock estimates by state for the total private economy and for total manufacturing. To calculate a state's average investment flow, we subtract the NCHRP stock value for 1970, the earliest year available, from the 1977 value, divide by 7, and divide this average flow by average state income for the period. ANOTHER source of private sector investment comes from MUNL, 1990, APPENDIXA. Like NCHRP, MUNL begins with the BEA National Capital Stock Estimates for Industries. However, MUNL allocates these to states differently than NCHRP. For example, national manufacturing capital stocks are allocated using state weights constructed from the gross BOOK value of depreciable assets. The total private capital stock in a state is estimated as the sum of stocks estimated for each sector in the state. To calculate a state's average investment flow, we subtract the MUNL stock value for 1969, the earliest year available, from the 1977 value, divide by 8, and divide this average flow by average state income for the period. The Criffield and Pangabean MEASUREMENTS differ fundamentally from the NCHRP and MUNL estimates. Criffield and Pangabean measure actual investment flows by metropolitan area. Investment flows from NCHRP and MUNL are state aggregates estimated from state and national data. Sources also differ. The Criffield and Pangabean data come from the Census Bureau, Census of Manufactures, whereas NCHRP and MUNL are based primarily on BEA estimates. Despite their similarities, NCHRP and MUNL use fundamentally different allocation schemes, which could affect estimation of EQ. 1. 630. J.B. Criffield, MPH Pangabean/REG Sci Urban Econ. 25, 1995, 607-630. References. Aschauer, D.A., 1989, Is Public Expenditure Productive? Journal of Monetary Economics 23, 177-200. Criffield, J.B., 1989, A Structural Empirical Analysis of Metropolitan Labor Demand, Journal of Regional Science 29, 347-371. Criffield, J.B., 1990, Manufacturing Supply, A Long Run, Metropolitan View, Regional Science and Urban Economics 20, 327-349. Criffield, J.B., J.F. Geertz, and S. Maida, forthcoming, Economic Growth in the American States, The End of Convergence, Quarterly Review of Economics and Finance, in Press. Criffield, J.B., and MPH Pangabean, forthcoming, Growth and Convergence in U.S. Cities, Journal of Urban Economics, in Press. Duffy Dino, K.T. and R.W. Eberts, 1991, Public Infrastructure and Regional Economic Development, A Simultaneous Equations Approach, Journal of Urban Economics 30, 329-343. Garcia Mile, T. and T. J. McGuire, 1992, the contribution of publicly provided inputs to states' economies, regional science, and urban economics 22, 229-241. Garcia-Milha, T.T.J. McGuire and R.H. Porter, 1993, The Effect of Public Capital in State-Level Production Functions Reconsidered, University of Illinois, IGPA Working Paper 24. Godfrey, L.G., 1989, Misspecification Tests in Econometrics, Cambridge University Press, Cambridge. Holtz-Eakin, D., 1991, Public Sector Capital and the Productivity Puzzle, Draft Manuscript, Syracuse University, July. Holtz-Eakin, D., 1992, State-Specific Estimates of State and Local Government Capital, Draft Manuscript, Syracuse University, January. Hulton, C.R., and R.M. Schwab, 1984, Regional Productivity Growth in U.S. Manufacturing, 1951-1978, American Economic Review 74, 152-162. Hulton, C.R., and R.M. Schwab, 1991a, Public Capital Formation and the Growth of Regional Manufacturing Industries, National Tax Journal 43, 121-134. Hulton, C.R., and R.M. Schwab, 1991b, Is America Really on the Road to Ruin? The Public's Capital, 6-7. Mankey, N.G., D. Romer and D. N. Vey, 1992, A Contribution to the Empirics of Economic Growth, The Quarterly Journal of Economics 107, 407-437. Munnell, A.H., 1990, How Does Public Infrastructure Affect Regional Economic Performance? New England Economic Review, September/October, 11-32. National Cooperative Highway Research Program, NCHRP, 1994, Project 2-17, 3. Macroeconomic Analysis of the Linkages Between Transportation Investments and Economic Performance, Final Report, the Johns Hopkins University, Institute for Policy Studies. Solow, R.M., 1956, A Contribution to the Theory of Economic Growth, Quarterly Journal of Economics, February, 65-94. Tatum, J.A., 1991, Public Capital and Private Sector Performance, Federal Reserve Bank of St. Louis Review, 3-15.